So in this lesson, we're going to do a couple of Hess's law problems to get familiar with using a combination of reactions to achieve a desired result. Okay, so our reaction of interest today is C2H4 gas plus 6F2 gas to produce 2CF4 gas and 4HF gas. Okay, so we want to know the enthalpy of this reaction. To do that, we're going to use the following three reactions. We have H2 plus F2 to yield 2HF gas. I do apologize, those are in the gas phase. Okay, so the enthalpy of this first reaction, delta H, is equal to negative 537 kilojoules. The second reaction that we can use to achieve this is carbon plus fluorine gas to yield CF4 gas. So our delta H for this one, negative 680 kilojoules. And then finally, the third, we have carbon, sorry, that's solid, plus hydrogen to give us the C2H4 gas. So delta H here is equal to 52.3 kilojoules. Okay, so when I start a Hess's law problem, I like to look at what I have and look at what pieces I can get set. And what I mean by pieces to get set is I look at what I have here and try to look and see if there's any equation that just has one of those particular things. So for example, C2H4, I notice that reaction 3 has C2H4, but none of the other reactions do. So I can use this to set C2H4. So remember, the whole process of this is to try to yield this. So first of all, things need to be on their proper side. And second, they need to have the proper coefficient. So I need this to have a coefficient of 1, but I don't want it to be a product. I need it to be a reactant. So I know when I do this, I'm going to reverse reaction 3. So I'm going to R reaction 3. I'm going to take 3 and reverse it to get the C2H4 gas, arrow 2 carbon plus 2H2 gas set here. Okay, so when I reverse this reaction, I know my delta H. I'm going to get the sign change here. So delta H is now equal to negative 52.3 kilojoules for this reaction. Okay, so now this here, this piece I just did, looks exactly the same as the piece in my reaction. So I have set this in place with the proper coefficient. Okay, so let's take a look and see if there's anything else that we can do that with. I see carbon is in a couple of places here, and it's not up here. Let's see, it looks like CF4. We can set now, say CF4. Okay, so for CF4, I notice it's on the product side, which is great because here it's on the product side. So all I need to do is get the coefficient to be the same. So to get these two to look exactly the same, I'm going to need to multiply reaction 2 by 2. So I'm going to times 2 reaction number 2. So I get 2 carbon plus 4 F2 arrow 2CF4 gas, and I know my delta H is going to be double, so I'm going to have 2 times negative 680, and we'll put our kilojoules there. Okay, so after this step, now I have 2 CF4 gas, which is identical to what we have up here, so now we've set this piece in place. Okay, so the last one I see 4HF. So it looks like I can use HF here. And since this is my last reaction, I'm going to set HF based off of its coefficient, and then I'm going to check to make sure everything works out by getting my carbons, hydrogens, and fluorines to do kind of what they need to do. Okay, so to set this one, it's on the proper side. They're both products. I just need this coefficient to match this one. So I'm going to have to multiply reaction 1 by 2. So multiply by 2 reaction 1 to give me 2 H2 gas plus 2 F2 gas and 4 HF gas. And my delta H will be 2 times negative 537 kilojoules. Okay, so if I take a look here, I have that 4HF gas, which matches up here that 4HF gas. Okay, so now hopefully we can go through and eliminate things that are equal on both sides, called intermediates, or kind of like in ionic equations, we call them spectators. Okay, so let's take a look. All right, so we have carbon, 2 carbons on the product side and 2 carbons on the reactant side here. So products here, reactants here, those cancel each other out. Okay, so those ones eliminate one another. I see I have 2 hydrogen gas as a product, and now I have 2 hydrogen gas as a reactant. So those cancel each other out as well. For my fluorines, they're on the same side. They don't cancel each other out. They're going to add together. So 4 plus 2, this tells me I have 6 F2 gas. So if we look up at our original reaction, that 6F2 is what we needed to happen here. So our fluorine worked out, and then all of our extra added sort of species here also ended up canceling each other out. So if we add all of our remaining pieces together, we have C2H4 gas, nothing else from here. Those were eliminated. Over here, we combine those. We have 6F2 gas. On the product side, we just have these 2 remaining, 2CF4 gas and 4HF gas. So my delta H is going to be the sum of all of these, so negative 52.3 kilojoules plus 2 times negative 680 kilojoules plus 2 times negative 537 kilojoules. Okay, so I'm going to take those and I'm going to sum them all together. Okay, so when I do that, I get that the enthalpy of this reactant is negative 2,486 kilojoules. Okay, so I use those separate 3 reactions there to actually find the enthalpy of my desired reaction by using the pieces of these 3 reactions here, getting things to sum together and getting different things to cancel. Okay, so the way Hess's law works, we'll do sort of a quick little diagram down here. If we were to look at energy, and so we have negative, so we know this is exothermic. So if energy was here, let's put our reactants up here. So this will be reactants. Okay, so we start off our reaction. We have the C2H4 gas and the F2 gas. Okay, so we'll even put the 6 there and 6F2. So we have the reaction in the vessel. We're starting with these 2 things. So let's kind of look at how this reaction proceeds. So if it just sort of reacted all at once, we know then that our products would be down here. So our products would be down here. Our products are the 2CF4 and the 4HF. So they're at a much lower energy state than we had up here. And we had an enthalpy change of negative 2,486 kilojoules of energy were released to go from here to here. Okay, so if we look at the pieces that we have here, we could kind of look at this as sort of a stepwise type of thing to get from here to here. So you can kind of think about what happened with reaction 3. So in reaction 3, if we kind of go up there and look, it looks like this was busted up into its elements. So we can kind of think about that. So the result of reaction 3 is now we have 2 carbon and 2 H2 gas when this essentially decomposed into its elements, and we still have those 6 F2 gases because they haven't reacted yet. And that first enthalpy change we see up here, that was the negative 52.3. So we can put our negative 52.3 right here. So that's kind of like one of our first steps that happened here. Okay, so this became this and this. Okay, so we'll do our second one now. So our second step now from here, we can pick, now we're forming from these pieces, we're forming now the products. So let's say we're forming the, I don't know, CF4 first. So we're going to combine some things here. We're going to have now 2CF4 that have combined. Okay, so 2CF4. So we should also then have, so we're combining the 2 carbons with now 2 times 4 with 8 of our fluorines. We should still have our 2 H2 gas remaining, and this should leave us with now 2 F2 gas remaining. So again, combining carbon and fluorine to make our first product, our CF4. So our enthalpy change here was from reaction number 2. That was that 2 times negative 680. Okay, so to make our CF4, that was that 2 times negative 680. And then probably didn't draw this very good to scale, but then that last drop we have there. Now the hydrogen, the 2H2 and the 2F2, those now are combining to now form our final thing, our HF. So from here down, then we have our final products where now we have only the CF4 and the 4HF. And this was the 2 times negative 537 kilojoules here. So again, if we kind of look at the reaction in steps, we can kind of see what happened here. So here, just you consider the full reaction, this turning into these products, this is the energy. But if you kind of look at the steps that happened, you have your carbons combining with the fluorines. So if you just look at that first step, or breaking things up into elements, and then you have things combining to make products, your carbons and your fluorines coming together, and then finally your hydrogens and fluorines coming together. These individual steps sum up to give us the overall change in enthalpy of the reaction. Okay, so that's how Hess's law works. If you can't measure it directly, if you can measure the steps of the reaction, then you can combine them together to get the total enthalpy. Okay, so let's do one more nice practice problem here. So sometimes the enthalpy is not that easy to do. Sometimes the reactions get a little bit sort of crazy, and sometimes also involve fractions. So that's what we're going to do here for this one. So our desired reaction is FeO, solid, plus carbon monoxide to give us iron and CO2. So we want to calculate or find the enthalpy of this reaction. So the 3 reactions we have to build from are kind of a little bit odd. So for the first one, we have 3 Fe2 O3 solid plus CO gas to give us 2 Fe3O4 solid plus CO2 gas. Okay, so for this one, the delta H of this reaction is negative 47. So these are in units of kilojoules. Okay, so our second reaction is Fe2O3 solid plus 3CO gas to yield 2 Fe solid plus 3 CO2 gas. Okay, so for this one, our delta H is negative 25, and again, units of kilojoules. And then finally, number 3, we have Fe3O4 solid plus CO gas to yield 3 FeO solid and CO2 gas. So our delta H for this one is 19 kilojoules. Okay, so here's the reaction we desire with these 3 steps here. So this one's a little bit trickier to see because if you look at it, it's just carbon dioxide everywhere, and then there's carbon monoxide also everywhere. So we have to kind of look to see what we can start with or how we can just anchor or set something to get us going. So what I noticed first is the FeO, that's only in one spot here. So if I look, there's no FeO or iron 2 oxide anywhere except for right here. So I can use reaction 3 to put this into position, with the correct coefficient there. Okay, so let's do that. So in order to get this now from a product to a reactant with the proper coefficient, I'm going to have to multiply that reaction by 1/3 and reverse reaction number 3. Okay, so multiply by 1/3 and reverse reaction number 3. Okay, so when I do that, it's going to turn this into FeO. My CO2, that's going to turn that into 1/3 CO2 gas. Okay, if I look over here, I'm going to have 1/3 CO gas, and I'm going to have 1/3 Fe3O4 solid. So my delta H, I reversed it, so now the sign is negative. And then I multiplied by 1/3, so negative 19/3. That is my coefficient now, or my enthalpy for reaction 3. Okay, so I put this right here, and it has the proper coefficient on the proper side, so that's good. Okay, so again, introduce some fractions here, so this is going to be fun. All right, let's see what else we can use to maybe set or anchor something. I do notice that iron, we have compounds here. We've already used this one. This one is the only one that has iron. So it's already on the correct side, but I need to turn this 2 into a 1. So I'm going to need to multiply this by 1/2. So we're going to do 1/2 of reaction number 2. Okay, so that's going to give us 1/2 Fe2O3 solid. It's going to give us 3/2 CO gas. 2 divided by 2 gives us just Fe solid. And then we get 3/2 CO2 gas. So now our delta H is equal to still the negative 25, but now divided by 2 since we multiplied through by 1/2. Okay, so we'll use green here. So we have this on the product side with a coefficient of 1, just like in our reaction above. Okay, so that let us kind of deal with reactions 2 and 3. So hopefully now, whatever we need to do with reaction 1, we're going to bring all of this together, which it seems kind of hard to believe with all of these fractions everywhere, but it will work itself out. Okay, so let's take a look at reaction 1. So I do notice I have Fe2O3 and I also have Fe3O4. Okay, I do notice that these are going to have to be gone. Okay, I'm going to need to have these cancel each other or cancel out with the Fe2O3 and the Fe3O4 up here. Like, these can't be around anymore. So they're going to have to kind of be like our spectator ions. They're going to have to be eliminated. Okay, so the first thing I notice in reaction 1, if I'm getting Fe2O3 to be eliminated using this, I know for sure reaction 1 has to be reversed. To get this to cancel with this, I'm going to need this to be on the product side. Okay, I know I can't reverse this one because I've already used it to set my iron. So that leaves all the work with this one. So for sure this has to be reversed. So let's put our R down. Okay, so we know for sure reaction 1 has to be reversed. We also know for sure it's going to have to be multiplied through by some sort of coefficient that's probably not going to be a very pretty one. Okay, so when we reverse that, that's going to bring this over here, and it's going to bring this over here. So that's good. So we know they're going to be on the proper side to cancel here and here. Okay, so I need also for this to cancel with this, I need this 3 to be a 1/2. Okay, so I need this coefficient of 3 to be a 1/2. I need this coefficient of 2 to be a 1/3. So the actual magical answer, the least common multiple of 2 and 3 is 6. So we're going to multiply through by 1/6. Okay, so 6 is something that works for both of them. Okay, so when we reverse that, our CO2 is going to be now brought over here as a reactant. So we're going to have 1/6 CO2. Okay, so then we're going to have this. So 2 times 1/6. So we're going to have 2 over 6, which gives us 1/3. So we're going to have 1/3 Fe3O4. And we'll have our arrow. Okay, so now let's look at these here, the reactants that are now our products. This one's easy. This will be just 1/6 CO gas. And then this one here, we're going to have 3 over 6. So 3/6, which is 1/2. 1/2 Fe2O3 solid. Okay, so the delta H for this one, for reaction 1, we reversed it. So now it's not negative 47, it's positive. And then we multiplied through by 1/6. So we'll have 47 over 6 for our delta H. Okay, so now the moment of truth. Of course, everything hopefully now should work out and cancel. So it seems kind of like a stretch here, but let's take a look. Okay, so we have those. We know those are good. We have 1/2 Fe2O3. And over here, we have 1/2 Fe2O3. So again, a reactant and a product, same coefficient. Those cancel. Good so far. Okay, so our 1/3 Fe3O4, 1/3 Fe3O4, that cancels with that. So it looks good so far. Okay, so now we're going to deal with the CO2 and the CO. Okay, so if we look over here, we have 3/2 CO. Okay, so that's CO2, that's CO2. If we look over here, in terms of CO, over here we have 1/3 and 1/6. If you did some common denominators and added those together, 1/3 plus 1/6 is 1/2 CO gas. Okay, So this is one of those things where we're going to get some partial canceling. Okay, so we'll do our arrow. Okay, so half of the CO2, 1/2 CO2, will cancel with 1/2 of CO2 here. So this will cancel with, we can turn this into 1 and 1/2. So that 1/2 will cancel with this and leave us just with 1 CO gas on the reactant side. Okay, so 1 CO because half canceled with a half there and left 1 behind. Okay, so let's now look at CO2. We're probably going to find a similar situation there. So if we look at our CO2, we have 1/3 plus 1/6. So we have 1/2 CO2 on the reactant side. On the product side, we have 3/2. 3/2 CO2, which again we know is 1 and 1/2 CO2. So half CO2 cancels with half CO2 and leaves us with 1 CO2 gas remaining. Okay, so if we now combine all of this together, we have our FeO. Okay, we said 1 CO gas remains on the reactant side. So we have our arrow. Then on the product side, we have our iron. And then we said we had 1 CO2 gas that remains on now the product side. Okay, so we did it. Everything magically canceled. We got this is the same as this. Okay, so now for our delta H, that's -19/3 plus -25/2 plus 47/6. Add that together, we get -11. So the enthalpy of this reaction here was -11. So this problem here was a little bit difficult, but it did introduce a couple of things that we do often see in enthalpy reactions. The first one being fractions. So these fractions, each and every one of them having a fraction, made this problem especially difficult. So this would be like a challenge question. This one's definitely for sure quite rough. But also sometimes we have equations that are introduced in a Hess's law cycle that they're really one of their main purposes is to eliminate something that doesn't have to be there or isn't there. So like, for example, equation 1's main purpose or one of its main purposes was to eliminate the Fe2O3, okay, that we introduced in equation 2. So this helped us eliminate this. And again, this helped us eliminate this here. So unlike the previous ones we did where we were able to get a major piece of the equation and set it, this one didn't do that. So this one had an equation that was almost sort of serving as an elimination to get rid of all of this extra stuff that we had introduced along the way. So you will encounter problems like this, especially as you work through those extra credit worksheets, where we do have to have, again, sometimes some equations in a Hess's law cycle are simply there to help you eliminate things that aren't supposed to be there.